G'day, my name is Brennan Gregg, and welcome to my talk. I work at Netflix, and we're deployed on AWS for our cloud. It's very large, you may have heard of it. And that's running Ubuntu Linux. We also have a CDN that's based on FreeBSD, that's physical servers. Netflix is an awesome place to work, and the team I'm on is the Performance and Operating Systems team. Our job is to evaluate technology, and times like reInvent keep us all very busy with all the new announcements. We come up with recommendations and best practices for the Netflix cloud. As part of the work that we do, engineering work, we often have to create new tools, especially observability tools to fill in missing gaps. And we will often open source those tools. We help with projects, new rollouts of technologies and applications. And we can also do incident response if there is a performance issue. My manager, Ed Hunter, is in the room, is here at reInvent, and we're actually hiring a couple of positions, so you can come join me and work on my team at Netflix. We'll all be at the booth after this talk, the Netflix booth. In this talk, I'm going to go through how we do performance tuning of EC2 at Netflix. I give many talks where I'm covering what I do with kernel analysis and kernel tuning, and I'm getting into the nuts and bolts of the system. This talk's a little bit different. Instead of covering what I do, this is more covering what my team does, the team that I'm on, the Performance and Operating Systems team. And so this isn't just about kernel tuning, it's also about instance selection. It's about understanding Amazon EC2 features, tuning methodologies, and all the observability and analysis that we do. I'm going to cover some tunables in the next hour. Think of it as this is what's in our medicine cabinet. These are best before 2018. If you're looking at this slide deck from the distant future, these tunables may not be a good idea. So tunables is something that does need to be revisited. So instance selection is the first topic I'll cover. Just as background for the Netflix cloud, we do have many different workloads. So we have Cassandra, EV cache, applications, we're using ELBs. Within the applications, there's many workloads as well. So we have proxy servers, we have API servers, we do media encoding, recommendations, and big data. Our Amazon AWS environment is wonderful to do performance analysis and tuning on because of how it's configured to do red-black auto-scaling groups and how we can take traffic from an elastic load balancer and send it to a canary. We can look at a performance tunable and begin by sending it to a canary. That may be just one instance. And then see how that performs with some real workload. Netflix has a library, Hystrix and other libraries, to make sure that we do fault tolerance. If, as part of doing a performance experiment, we actually break those requests, those customer requests, these will automatically time out and then go to a backup service. And this can happen so quick. If you're browsing Netflix, you may not even notice that your session was canaried because we're doing a tuning experiment. If it failed over within 100 milliseconds, you may not notice. So it's a very safe environment for doing these experiments. That's great for a performance engineer. We can spin up a canary, we can try out some tunable parameters. If it looks good, as part of the regular deployment model, we launch a new auto-scaling group with instances, and then over time we shift the workload from the old auto-scaling group to the new one. And if things go wrong, we can move it back. This is great. We also do use micro-benchmarking, but micro-benchmarking isn't the only tool. We also get to play with real load workloads. And it's because of those libraries and our architecture that enables us to do that. So we have many different ways of understanding whether tunables are going to be effective. For instance selection, there are many instance types. And the instance type itself, in some ways, is a tunable parameter. Before cloud, we had mainframes and data centers. And you purchased some big iron, a very large server the size of a fridge, and you had to tune it. you couldn't swap it out because you discovered a month later you bought the wrong server. But with Amazon EC2, the instance types can be replaced very quickly. And so we aren't locked into years of a support contract for that instance type we've selected. And so that way, the instance type itself is a very major tunable parameter. What instance type are we going to pick for each of the different workloads? And so we at Netflix, we're actually using over 30 different instance types to run the different applications. And I've listed some of them here that we should be pretty familiar with. How do we actually pick an instance type for a workload? There's a few different ways, and the first one, I've drawn an instance selection flowchart, although at Netflix, this is something that the engineers have in our heads. We don't draw this out on a whiteboard. We know this stuff off by heart. And this way, we're looking at characteristics that would point to a particular instance type. If you really need large disk capacity, terabytes of disk, we can deploy on D2s, and so have those many terabytes of hard disk storage. If you don't need that much disk capacity, and only some Netflix microservices are heavy users of disk, like the databases, then is it disk I/O bound? Is the performance workload bound or limited by disk I/O, disk IOPS? If it is, then we look at whether it's cacheable or not. What is the working set, which is how much of the data is accessed frequently, say within an hour? If it can cache, we may be better off trying to cache it in main memory, DRAM, and then picking an instance type like an M4 or an R3. If it can't cache, then we're going to pick the best storage instance type available, currently an i3, with NVMe, SSD devices. But for some of these, it's going to end up being a choice between whether we want to go memory or CPU, and if it's memory, it's R3 instances, and if it's CPU, it's C5. At Netflix, we do actually have a lot of M4 instances, so they're very popular. A different way of picking an instance type is to determine what is the bounding resource. And so whether that's CPU disk or network I/O, and pick the instance type just based on that alone. That can be found using estimation. I know it's a database. I know it's going to have high IOPS. I know I should probably pick an i3. We can use an existing real workload. We can canary a workload onto an M4 and then see which resource it's really hitting and then pick it based on that. And we can also do a benchmark or load test experimentation to figure out what should be the bounding resource for a synthetic workload. And then we choose the instance type based on that. We have a tool, Nomogram Visualization tool, written by Scott, who's here, and that lets us pick the characteristics we're interested in, so the attributes that may be the performance bounding resource, and then the classes we're interested in, and then it will tell us the options available. It also gives us the prices, which I've had to redact because I'm not sharing, that's up to Amazon to share prices, that's not for Netflix to share. So that helps us pick which of these instance types best suits workload, given the attributes we know are important. There's another way we could pick instance types as well, which is fun to mention, and that's a brute force approach. In the past, Netflix has done this, and that is where we're able to run the load on all available instance types, spin up one instance type for one instance for each instance type, and then use the ELB to fan out the workload, and then measure price performance, and then find out, using a brute force approach, which instance type delivers the best price performance. That's interesting. We don't currently use it. I think that tool fell out of repair. One problem with it that you'd have to pay attention to is you may find you've picked an instance with the best price performance, but you've neglected some other attribute that's important. For example, latency requirements. You may find this has the best price performance, but all the API requests are taking over 1 second. And so customers wouldn't be happy with it because latency isn't part of price performance, if that's the only thing you're looking at. And so it's important to think that there are other requirements as well. And I just graphed this to show that as you increase throughput, there's a point where it's clearly unacceptable, and there's a point we'd like to roll it back so that we have some headroom. That's really where we're looking for where we'd want to measure price performance. This is an acceptable latency for price performance, just in case you want to try this approach. That's how we pick instance types to start with. What about reselection? We have tools that we can use to see our instance usage. And I've had to redact the instance types, but this quickly does a list of this is the most common instance type in Netflix, whether that's an M4.8XL or whatever down the list. And we use this tool to see if there's any old instance types that need to be upgraded, because performance and price performance always gets better. Instance cost, which we also track regularly by auto-scaling group and application and instance types, and I've had to heavily redact this, but we have tools for this as well, so we can understand the instance cost and to see where our tuning efforts are best spent. As a performance engineer, there's lots of things you can do to tune applications and EC2, and so it's important for our team to focus on the highest priority or the biggest spend applications and to tune those first. Another thing to look out for is instance variance. So we may pick an instance type, everything looks fine, but there is a problem a few weeks later when main memory gets populated or when the storage gets full, and then things to perform badly, or some instances begin to perform badly. And so we have ways to quickly look at the performance of different nodes within an auto-scaling group and to see if there's any outliers. That may also tell us that we should revisit instance selection and that there's a problem. Amazon EC2 features is another important area of tuning that we pay attention to. And this is also an area that became quite confusing because Xen, over time, the Xen hypervisor has provided different modes for operation. So there's been power virtualization, PV, and hardware virtual machines, HVM. And then you could also boot a HVM instance, but then use a PV driver. And then there's PV HVM. To try and make sense of this, I've drawn a diagram so that as part of our team is to always understand Amazon EC2 features and especially hypervisor features for performance. And so this is something that I've spent time on and had help from other people. The diagram looks like this, and it's based on an original Xen modes diagram from Lars Kurth. And George Dunlap then published that diagram on the Xen wiki as a blog post a few years ago. And what I've done, I've been editing this diagram and tweaking it, moving things around. I've added extra columns so that we can properly understand the state of hypervisor and virtualization today. This really tells the story in one slide. To start with, the first row I've got there shows what happens if we're fully emulated. So imagine the bad old days of the first x86 hypervisors. It was great that it was possible, but these had to use binary emulation and binary substitution of instructions in order to work. In those days, this was before processors had hardware virtualization support, like Intel's VTX. Hardware virtual machines got a very bad rap from those early days. And those early days, I mean, virtualization, x86 virtualization started in the late 1990s with VMware, 1998. But over time, both in software of the hypervisor and also in hardware for the CPUs, the network interface cards, the storage interface cards, the storage adapters, these have all come up with ways to improve performance. In software, ways to improve performance usually meant para-virtualization support. And that's where instead of running an unmodified guest, the guest now runs code that is aware that it is running as an instance under a hypervisor. And that hypervisor can expose hypercalls, which are efficient ways to access resources, and then a para-virtualized guest or code in a para-virtualized code in a guest can then make hypercalls and improve efficiency. The first line I've got here beyond fully emulated is Zen 3.0 vintage, and this is showing, when I first joined Netflix, this is actually showing when I first joined Netflix in 2014, this is what most of our instances looked like. So going along that line, we've got CPU memory. At this point, we're past VTX. So the processors had support for hardware virtualization of privileged instructions and also for page table operations. And so the performance overhead was very small. It's near metal performance. Then on those instances, we had paravert drivers for network and storage devices. I was at Netflix when we began rolling out HVM instances using PV-HVM drivers. PV-HVM drivers are para-virtualization drivers that are designed in a post-VTX era. VTX is the processor hardware virtualization technology. And so these drivers can make use of hardware virtualization. So in a way, it's getting the best of both worlds. You're getting software optimizations, paravert, and you're making use of the hardware optimizations from the CPUs. So that was PV-HVM drivers. We often got those PV-HVM drivers. Part of the confusion was that the way Amazon exposed it was in terms of how the instances booted. And so you needed to select between PV or HVM. When the instance was up and running, your HVM instance may be running with PV drivers, which is what I'm showing here. And your HVM instance may be running with PV-HVM drivers. I wrote a blog post because this is all so confusing. There's so many terms here. And at Netflix, part of our team is we have to understand this and we have to explain to other engineers what you should be picking. And an epiphany is, in some ways, this is not picking options to deploy instances. This is showing the transition over time. So as Zen improved performance and added new capabilities, and as Amazon and the EC2 teams, engineers also added capabilities, instead of things you should pick, it's simply what version hypervisor are you on. And so that's why I've ordered these rows from old to new. Moving forward to the Zen AWS 2013 offerings, this is where we then had I2 instances with the SR-IOV networking. So now I can take the network I/O column, and that has hardware virtualization support. So network I/O workloads became very fast. And then this year, for Zen AWS 2017, the i3 instance types also let you do local storage as SR-IOV. So this is near metal access. So this is where the card itself, the hardware card, understands virtualization and can create virtualized instances that guests can directly access. That's great. And I'd been working on this diagram, and I was really happy. It's like, finally, I can explain this all. I can write this blog post and explain this transition from the fully emulated world, which some people still, when they hear hardware virtualization, they think fully emulated. That's not what we're running these days, to coming up to today, to 2017. And then AWS threw a spanner in my works in terms of writing a blog post that explained it all by releasing a new hypervisor type very recently for the C5s. Now, I've been studying that. It's really interesting. There is a talk tomorrow by AWS. So Anthony Lugori is giving a talk on the new C5 hypervisor, which I recommend attending, as he's the authority and he'll be able to explain exactly what they've now done. Since the C5 has been launched, I have been using them, and I can say it looks like some of the key advantages are, with the previous instance types, you had to make sure you selected to use the hardware virtualization drivers, but this now looks like that is the default, so it's easier to use. And it also looks like interrupts have hardware virtualization support as well. And if you've been following virtualization, interrupts have been described as the last battleground for making hardware virtual machines perform at near metal speeds. The previous battleground was SR-IOV, making sure that we could have direct access to devices, we could have DMA ring buffers to talk to devices. But then when devices talked back to the guests, they're making interrupts. And it looks like that's now been fixed with the C5 hypervisor. Amazon has also mentioned that that hypervisor may be used for other instance families as well, which is really exciting. So I said there's a talk about this tomorrow, and I am going to do a blog post after that talk where I cover this all in more detail. So please check that out. So at Netflix, what does it mean we should pick? It means we should just pick the latest. So the latest offering, if it makes sense for that workload. So if we want an M4, am I picking HVM with PV drivers? No, I'm going to pick the best. I want to pick boot on HVM with PV HVM and SR-IOV. Or if it's the new hypervisor, I'll go with that because I'll get those things set up automatically. So I talked about these. So networking SR-IOV, that's where the network cards can expose virtual instances so the guests can have near metal access. I noticed on some of the vendors who make these cards, if you read the spec sheets, they call it bare metal access. And they're the ones that actually built the card, so maybe I should be calling it bare metal access. So I've called it near metal access. And for EC2, the IXGBE driver supports up to 10 gigabits per second, and the ENA driver is 25, which is pretty great for a cloud instance. And then storage SR-IOV, that's what was launched this year. And Amazon called the network SR-IOV enhanced networking. I think we should call this enhanced storage. So far, some instance types only, and does use NVMe and VTD for I/O virtualization. So which should be called bare metal disk access or near metal disk access. And we've already, on our team, we've done benchmarking and found an i3 can exceed 3 million disk storage IOPS, which is pretty exciting. Kernel tuning. So we've picked an instance, we've picked our SR-IOV drivers, or we're using the latest hypervisor. Now comes time to tuning the kernel itself. To start with kernel tuning, we're typically looking at 1 to 30% wins for average performance fines. This adds up to significant savings for the Netflix cloud, so we do care about it. But in context, if you're doing application analysis, you can find 2x wins and 10x wins. And so at Netflix, while our performance team is always doing analysis around the stack, many engineers at Netflix on the application development teams, they're doing their own application performance analysis. And so they're finding those very large application wins, eliminating unnecessary work. But we still care about performance across all the layers down to those small wins. Now, 1 to 30% for Netflix is a lot. For you, it may not be much. So you may think, I don't care too much about kernel tuning. You do get bigger wins when you're reducing latency outliers. And that may be important because you're trying to meet an SLA. I need to take my 99th percentile latency down, and there's no way around it. I have to tune everything and make this work. And so if that's a problem for you, that's a situation where everyone's doing kernel tuning because you have to. We deploy tuning by baking it into our base AMI, so everyone gets it. We have had experimental tuning package add-ons in the past to play with. And we do workload-specific tuning for applications. Of course, remember to tune the workload with the tunables. If I improve the performance of the storage devices, if I improve the buffer sizes or read ahead or storage I/O sizes, I may need to also tune the application so that it makes use of that new capacity. So I wanted to mention that. I'll go through these tuning targets quickly. The CPU scheduler, You can tune the scheduler class, priorities, migration, latency, and task sets. Some applications benefit from this, including things like tuning the scheduler migration cost. The Linux kernel tries to honor CPU affinity, and that is where a thread is running on a CPU, it's running with hot CPU caches, so level 1, level 2, TLB cache. If the thread is context switched off, and then wants to, because there's an interrupt or another application needs to run, and then that thread needs to run again, but that CPU is busy, do we pick an idle CPU and migrate the thread, or do we wait a little bit to see if the CPU will free up? There's a performance benefit from waiting a little bit because the CPUs are warm on that CPU. And so some of this can be tuned. The scheduler migration costs nanoseconds, and that can have a performance boost, especially for large NUMA systems, because now your caches are even more important to avoid talking over the remote memory bus. Some Java applications we've found have benefited from sched batch to reduce context switching as well, which you can set up using shed tool. Task set is another one which I often use task set for experimentations, and that's where I can reduce how many CPUs an application can use. If you're ever in a situation, actually I had this last week, where it was a micro benchmark and it was running at 1.7 million ops per second. Sounds good, running across 72 CPUs. I used task set and I reduced it to only run on one CPU, and then it ran at 3.2 million ops per second. As a performance engineer, I would not be deploying that in production because it tells me something bad has happened, something really bad has happened. If I'm going from 72 CPUs to one, and now it has double the performance. And the thing that was bad, which I did a profile in a flame graph, was that we were in lock contention. We're in lock hell. So the more CPUs that you added, the worse things got. And so it's one of those classical experiments you do as a performance engineer of reducing the CPUs, and if things go faster, you've probably got a lock problem, and you would fix the lock problem. So my point is task sets are useful for investigating CPU scheduler issues, but I don't think it's part of the final solution. The final solution is you fix the locking problem. Virtual memory. So we can tune swappiness, overcommit, the behavior. Swappiness, we set it to 0 to disable swapping. And we don't have swap devices configured for our base AMI. So when and we tune applications so that they don't run out of memory. We do have to look out for behavior out of memory killer, because what can happen is an application can grow by mistake and then get killed, and then we have to go around and tune it. But that's another area that we can tune. And of course the tunable for swapping helps you pick between the ditching memory and favoring the file system cache, or favoring keeping application memory in main memory. So do I want to make sure the application is in main memory, or do I want to move some out to a swap device to free it up for a file system cache? We just don't play that game at Netflix. We don't have the swap devices configured, at least on all the microservices I'm familiar with. Huge pages is another tunable parameter to be aware of. The CPU operates on memory in units of pages, which depends on the architecture. For Intel x86, it's 4K. That can be inefficient for large memory applications, and so processors for a long time have supported large pages or huge pages, 2 megs or 4 megs instead of 4K. There were problems in the past. So when we upgraded to a previous Ubuntu release, we found that the performance was worse because of transparent huge pages had some outright performance issues. And so we found that turning off transparent huge pages improved performance. That was the previous release. That was trusty. Now we're going to Xenial. We're turning this back on. So we're going back to madvise. But it's a tunable parameter to be aware of. It can affect performance. So whether it's using huge pages, transparent huge pages is whether it lets the kernel manage it so you don't have to explicitly set up regions. NUMA balancing, another tunable to be aware of. The worst I've seen was now fortunately, many instance types are so small they don't have different NUMA nodes. So if you run NUMA stat, you only get one node. But for the very large instance types, they are multi-NUMA systems, and you'll have multiple nodes. And then the kernel can spend time moving pages from one node to another. And when I say node, it could be a group, a bank of memory attached to one socket processor. And then there's another bank of memory attached to another socket processor. And if your application is busy running on one socket, you'd rather talk to local memory than going over the CPU interconnect. So the kernel doing this effort of moving pages of memory around to keep it close to where the application is makes sense in theory, but we did have it run so aggressively that the system was consuming 60% of all CPU cycles doing NUMA page rebalancing. So the system itself was, the application was secondary. This was a NUMA page rebalancing service that Netflix was spending a lot of money to run. So anyway, we turned that off. It's like, that's a bug. In later kernel versions, they have been improving this so we have more fine-grained controls. But another one to be aware of. File system tunables. So dirty ratio to dirty background ratio and expiry semi-sex, these control how quickly the write-back caching works. And so when the application does write to the file system, it doesn't immediately engage the storage devices. It can keep it in memory and then flush it later. And you can tune how aggressively it flushes that. Buffering is good. It helps the application continue. And we could also mount things using, say, no A time and discard no barrier, various other file system tunables as well that you should check. And we actually have ZFS on Linux running for our container microservice. And we also have Btrfs running for the container microservice as well. We're trying out both. And both of them come with many, many more tunables that you need to pay attention to. So if you have a workload that is file system bound, have a look at the tunables because there should be many. Storage I/O, the reader head size, the number of in-flight requests, the I/O scheduler, volume stripe width, these are all tunable parameters. If you have a workload that is storage bound, these can make a big difference. We've had that in the past with Cassandra being very sensitive to the reader head size, and tuning that to match Cassandra improved performance considerably. SSDs can perform better with the no-op scheduler. We don't need to have an elevator scheduler that worries about the rotational disk head as it moves around. We can turn that off because SSDs are different. And then tuning the MD chunk size and stripe width to match the workload. So there's a lot that we can do. When we have done some of this for Cassandra, and we've done some of this for the storage workloads. Networking we've done a lot with, and there's TCP buffer sizes, TCP backlog, device backlog, and so on. Very common to tune these. This is the current tunables we're using. Again, this could be out of date next year. And that involves increasing the buffer sizes so that we can improve network throughput. And the hypervisor itself, whether we're using the PV or HVM instances, PV or HVM AMI, these days it's HVM. In the very distant past, when HVM was first introduced, there were some performance issues, and so there became this. Some people had found that PV could run faster than HVM, and you'll still find this on the internet because nothing ever dies on the internet. All the old tuning advice is still out there. So if you try and search for PV versus HVM, you'll see some very out-of-date advice telling you that PV is faster. PV may be faster for some very corner case workloads, but nowadays it's the HVM instances. And of course, as I said earlier, once they boot, they may be using PV HVM. The clock source is something that we have tuned for a while. And so there are different clock sources available. And we encountered a Zen clock source regression in the past. And the best case was reducing CPU usage by 30% and average application latency by 43%, just by changing the clock type that our instances are using. And so that's TSC, and you can set that up. Why wouldn't that be default? in the distant past, processors couldn't guarantee that TSC monotonically increased across all cores, and so there could be clock skew and clock could go backwards sometimes. There were various concerns about TSC. Talk to Intel, talk to AMD, talk to your processor manufacturer and say, are these concerns relevant now in 2017, or is this old? Is this from like 1997? And so my belief is that wisdom is quite old-fashioned now, and so we can trust TSC. But beware of that. Check it out. Methodologies for tuning. So I want to cover some methodologies for understanding the performance of our workloads, since a lot of the tunables we'll end up using, whether it's kernel or application tunables, can be derived from how the system is performing, the observability metrics. We have dashboards at Netflix, for example, a Netflix Perf Vitals dashboard, which shows all sorts of statistics for a auto-scaling group or an application. So requests per second, how many instances it's using, which changes. As a performance engineer on auto-scaling groups, when you see performance change, it may not be that there was an application change or a workload change. It could be an instance change. Auto-scaling may have added 10 more instances and then fanned out work amongst a larger pool, which can cause a performance issue. So we always have to look at the instance count when we're trying to understand performance in the cloud. So this is using the Atlas cloud-wide observability tool. And so there's lots of metrics we can use for drilling into where the performance problems are. Java heap, whether it's latency, load average, 99th percentile. So that performance methodology is to look at a dashboard, which is almost like a checklist of options. Another methodology is to either do workload analysis or resource analysis. I think it's helpful to separate them and realize, be conscious that you're doing it. Resource analysis is where you're thinking of how's the CPU performance, how's the disk performance, how's the network performance. Oh, the disk performance is bad. Let's work our way up the stack. Is file system performance also bad, or is it all asynchronous? Now, how's the application affected? In some ways, it's nice to do that analysis approach because these resource types are well known and well understood, whereas your application may be custom, and there's no one else you can talk to about how that application works, whereas you can talk to everyone about how CPUs work and disks work. So there's some benefits from that approach. A disadvantage is you don't have application context. So you may often see a disk I/O performance issue, but you don't know whether it's affecting the application or the application request. The other way around is to start top down and begin with the workload analysis, what's the application doing, and then drill down into the libraries in the system call and the kernel. That's useful as you can then expose latency in terms of an application request. So you can always keep track of, does this matter? Is it actually hurting our requests? The use method is another methodology for doing performance analysis and tuning. This is one I came up with a long time ago. It's where I take a functional diagram of a system where I'll plot out the CPUs, storage devices, network devices, all the buses and interconnects, bridge devices. And then for every hardware and software resource, I want to check 3 metrics only, which is utilization, saturation, and errors. If you look at a lot of performance monitoring products, and if you look at the kernel itself, we're drowning in metrics. There's so many metrics. This is an approach that reduces that set to maybe 48. So just 3 metrics for each resource. It also reveals things you may not have looked at. So it reveals blind spots. How many performance monitoring solutions look at bus performance? Look at CPU to memory bus or CPU interconnect performance. I've had lots of issues with buses in the distant past, but many performance monitoring products don't analyze it at that level. And as a consumer of it, you wouldn't even know of it. You'd look at the performance monitoring product and say, wow, there's 1,000 metrics in here. Everything must be covered in here. But that's not true because it does have blind spots. This methodology helps you reveal and become aware of those blind spots because you can say, well, I don't have saturation for the CPU interconnect. So now I need to go find out how to measure that. So the use method poses questions to answer. And another methodology that I love to use, and that's on CPU and off CPU analysis, and we also use it on our team. With on CPU analysis, that's explain what's happening on the CPU. And so flame graphs are great at that. So do a flame graph CPU profile. I'll mention flame graphs in a bit. But if you're not on CPU, but you've got a performance issue, why are you blocking? Are you blocking because of resources, disk or storage? Are you blocking for locks? Are you blocking to simply sleep? Has the application developer added some sleeps in there that shouldn't be in there? Are you waiting for work, which is not a performance issue, it's just idle? And so being able to analyze the reasons why we block is useful as a methodology, because once you know you're not CPU bound, you're thinking, why am I blocking? And then you're using tools to explain why I'm blocking and to measure the magnitude of why you're blocking. I'll mention those tools in a bit. So the observability tools, how do we apply these methodologies? This is for discovering system wins that might be 5 to 25%, and application wins, which are much larger. There are lots of statistical tools that Linux comes with. We don't often use these at the command line because we have over 100,000 instances, and I mean, which instance would you log into? It's unusual that we know we have one instance that's a problem, and for some reason, workload hasn't automatically migrated off that instance. So statistical tools, it's important to understand these, however, because the graphical tools that we do use to examine cloud performance cloud-wide often use the same metrics. So if you look at SAR and you understand what's being exposed, you'll see the same metrics in GUI tools. So SAR is great. It has lots and lots of metrics. So here I'm looking at TCP throughput. I'm looking at active and passive TCP requests or connections. So active is where I'm establishing an outbound connection. Passive is where I have accepted it. And then metrics like retransmissions. And we use these, if we use these on an instance, which is rare, we do use these mostly normally. So the VM stats and the PID stats and the MP stats and SARs and so on. If you're in the situation where you do have to log into an instance, I did write a blog post with the performance team a while ago on performance analysis in 60 seconds. What's the top 10 commands you would run if you had to SSH onto an instance? So uptime, to look at the load averages, because they're not a great metric, but at least they tell you if things are getting worse or better. Demessage, because the kernel will often tell you if it's unhappy, if it's done something sad. And then VM stat and MP stat and PID stat and so on. System profilers, we do use a lot. We automate these through GUIs, so we don't have to log in. For example, using Linux perf to do CPU flame graphs, perf record minus F49 for 49 hertz, that's across all CPUs with minus A, minus G to get call graphs or stack traces. That writes a perf.data file. I can then feed it into my flame graph software and generate an interactive flame graph. On our team, Martin Spear has just published a new flame graph type. You might notice my old flame graph software there is written in Perl. Who likes Perl? There's still some of us. Yeah, how about that? So Martin has written flame graphs in a new language, D3, which is kind of exciting because with D3 gives us more interactivity. So I'm really excited for it, and my Perl program may become a thing of the past, and we all might be using the D3 version once we get it into our tools. So Martin finished that work recently and open sourced it and put it into the Google pprof profiler. It's pretty exciting. So if you notice Perl and you're a bit worried, don't worry, the D3 one is in the works. When I talked about flame graphs at reInvent 2014, this was the state of doing a CPU performance profile of Java. It was OK because we could look into the kernel and we could look into the operation of the JVM, but the Java context was missing. So the stacks were all broken because Java didn't honor the frame pointer, and the frame pointer is how the perf tool finds the stack trace. And the frame pointer wasn't honored as a performance optimization, which provides a minuscule tiny win on modern processors. I looked at hacking in the frame pointer, and so now, reInvent 2017, I can show how it looks. This is with the JVM with what became, so Oracle took my patch and rewrote it and integrated it as a tunable parameter. So it's now -XX plus preserved frame pointer. And so now we get to have the Java stacks. So our flame graph isn't completely busted. And you can see this is a mixed mode flame graph. You get to see everything from when the thread starts, we're running in the JVM, we're doing Java methods, then when we're going into the kernel. Hands up if you've used flame graphs before. All right, so we have maybe 15%. Flame graphs are awesome. We use them at Netflix all the time. The x-axis is the population. It's not the passage of time. The x-axis shows our full profile. The y-axis is the stack depth. And the color, here I'm using hue to identify different types of code. Green for Java, orange for kernel, yellow for C++. And what you do to interpret a flame graph is you just look for the largest towers, things that are wider. The wider it is, the more it was in the profile. The wide tower on the right looks like it's, I guess, 60% of the profile. That's consuming 60% of the CPUs. So this is directly proportional to the performance pain. So you simply look for the widest towers, and then you can understand the profile. We use them all the time. We've automated them. They're used by other companies as well. So Facebook has an implementation. I just mentioned we contributed flame graphs to Google's pprof. But I think they already had an implementation. ftrace is a tool for getting into other types of analysis. So flame graphs, we've used them so far for CPU analysis. ftrace lets us get into things like blocking and I/O analysis and deep kernel issues. It's been around for a long time. So it was first added in Linux 2.6.27. It didn't have a great front end. It did have some front ends. I wrote some very simple, easy to use tools and shared them as perf tools, which we've been putting in our base AMI, and I've been using to solve various issues. So just as an example of that, this is losnoop that uses ftrace, and that's showing disk I/O. So it's like TCP dump, but for disk. So instead of showing every packet, it's showing every disk request. And then I can look at the latency. Hugely useful for identifying patterns and really understanding what the disks are doing. Imagine trying to understand what the network interfaces are doing, but without using TCP dump. This is kind of what it's like to understand what disks are doing, but without using a tracer. It's crazy. You need to use a tracer. You need to see the device-by-device requests and to see the latency. Perf is another tool that's been around for a long time. That's what I was using for the CPU flame graphs, as perf can do profiling or timed sampling. Perf can also do tracing, and that's where it instruments software and we get an event per invocation of that software. So here I'm instrumenting consume SKB for when I'm consuming a socket buffer in the Linux kernel for networking. And now the stack trace is showing this is how I got to that kernel function. Great for debugging kernel internals. Can also do user-level programs and applications as well. The latest one in this field for tracing is BPF. So BPF, the Enhanced Berkeley Packet Filter, it has been enhanced so that it's now an in-kernel virtual machine that can take trace information and then summarize it in kernel where it's efficient, and then only asynchronously put the summary out to user level. Previously, we had things like ftrace, and we had perf for trace points, and we had kprobes and uprobes for dynamic tracing. But to do a lot with them, as a performance engineer, you had to worry about the overhead and whether you could do this in production. eBPF means we can do a lot of things we couldn't before. So I can do much more off-CPU analysis, and I can look at scheduler, I can trace scheduler events more confidently, knowing that I can summarize it efficiently and I don't have to worry too much about overheads. You always still have to worry about overheads, but it helps a lot. And so I've got a diagram just of the internals, but it shows you can write a BPF program The kernel can attach it to trace points, dynamic tracing or sampling, and then can export the information back to user level as per event data or as summary statistics. Just as an example of a tool, this is TCP Life, and it's showing each event summarizes one session on a system. And if I said, well, I want to see a list of what sessions are happening on an instance, you might say, well, you can use TCP dump for that. Surely there's a flag. What's special about this is it's showing things that don't go on the wire. So I can see the process ID in the command responsible for that session. I can see the millisecond duration. This is actually a nice tool. It uses BPF and it's open source as part of the BCC repository. It's also nice in that I was able to write this without tracing send receive. I instrumented just a kernel function called TCP set state to keep the overhead a minimum. TCP set state is relative to the rate of connections, not the rate of packets. So this is great. So we're starting to run this, and so different teams at Netflix have started to run this to get events, whether they're interested in security or network engineering, so that they can understand details of all the flows around applications at Netflix. Hardware counters is another observability tool worth mentioning, and there's two types. There's MSRs and PMCs. MSRs have been enabled for a long time, and they give us basic details. That's model-specific registers. And so I've used them to investigate things like turbo boost. Performance monitoring counters, PMCs, let us do all sorts of cool things, but they've not been enabled in the past on EC2. Here's an example open source tool I wrote for using MSRs that shows the real CPU megahertz. But PMCs let us do so much more. Early this year, Amazon launched a feature for the M4.16XLs and some other instance types that exposed the architectural set of PMCs. So these are 7 PMCs that give you a very high-level view of what the processor is doing. So you can investigate stall cycles by looking at the CPU cycles and instructions retired and looking at the IPC ratio between them and figuring out how much the CPU is stalled. You can look at last level cache references and misses and branch prediction as well and how well that's working. This is great. I wrote a blog post on it. I actually wrote a patch for Zen originally to add this to Zen, but Amazon went and did their own thing, which is great. But I'm having to rethink this all because now, with the new C5 hypervisor, the C5 hypervisor has access to all the PMCs, which is awesome. So we now get to look at, I've just run a very simple tool here, but there are hundreds of PMCs so that you can understand what the TLBs are doing, what all levels of cache are doing. They call it encore and uncore events when you're off the CPU and you're talking to devices or memory. Hands up if you've done PMC work before. So we've got like 5 people. So if you're based on the cloud, I guess I understand why you haven't, because you haven't had access, but it's something really cool. It's especially important because workloads are often moving to being memory bound. In the distant past, it was always disk I/O. Disk I/O was always killing performance. But now, after decades of engineering, disks are fast, SSD is fast, main memory is huge and caches things. And so a lot of the performance issues are now the memory buses and the CPU interconnects. And PMCs let you investigate that. That is a major area of performance issues nowadays. So there's a tool that we can now run on the cloud, Intel vTune. So just as an example of a new tool that you might hear about in the future, but it uses the PMCs to do this sort of analysis. But there's lots of open source tools as well. Netflix Atlas, I did mention, that's our cloud-wide monitoring tool that we use to look at our over 100,000 instances. And that's pretty great. It's very important that it works. We use it for incident response. And it has a lot of the OS metrics in there for analysis. And we quickly can do filters and breakdowns by region, application, ASG, or metric, or instance. Netflix Vector is a newer tool that we've been developing for instance analysis. And so this has a use method inspired dashboard showing utilization, saturation, and errors. But Vector is also great because it's where we can launch on-demand flame graphs. So we can click a button and get a CPU flame graph in a minute and quickly understand CPU performance. And I've recently been adding more flame graph types to do the off-CPU analysis using eBPF, which is awesome. So Vector is also open source like Atlas for analyzing low-level performance. In summary, that was a tour of what our team does, from instance selection, understanding Amazon EC2 features, tuning, and then methodologies for tuning and analysis, and many of the observability tools. Our team does a lot more as well because we often do get into Java internals and work with applications and understand performance in detail. These slides will be shared, and I've got lots of references and links. And I did mention I will do a blog post tomorrow where I do an extended version of the hypervisor diagram, and I'll explain each of the rows in detail. Because things are so confusing, and the new hypervisor, the C5 hypervisor, is adding even more things for us to think about. But I'll do a blog post to explain that. Of course, there is a talk tomorrow about the C5 hypervisor, which I recommend seeing, by Anthony Lugori. And there's also other Netflix talks at reInvent that I'd recommend seeing as well. I'll finish with, I can take a couple of questions, and then many of us will be at the Netflix booth today, and I'll be at the Netflix booth so you can contact us then. And the slides will be online. So, thank you.